So hello everyone, welcome to BVLSI lecture number 40, and today we are going to continue our discussion on resistive load NMOS inverter. So let's draw the diagram for resistive load NMOS inverter and its VTC curve. Alright, so first we'll draw its circuit diagram. So it consists of enhancement type MOSFET. We are drawing 4 terminal symbol. Alright, and here is my load, which is a resistor. Now I have to define where will my input go. The substrate terminal will go to the ground, so these two are connected to the ground. Now let us identify the terminals. This is gate, drain, source and body or substrate. Okay, so let's connect the remaining things. This is my VDD, supply voltage VDD. These two are connected to the ground. Input is applied to the gate terminal with respect to ground. So here is my input Vin. Output is taken across the drain terminal. So here is my output, and it is measured with respect to ground again. And this is my load RL. So the current flowing through the load RL, we can call it as IRL. And the current flowing through the drain terminal, we can call it as ID. Let me write it capital. Okay. So now let us begin with the analysis, and we have seen that last time from the observation we can check that input Vin is actually equal to VGS. Okay, VSB is equal to 0. Output Vout is actually equal to VDS. So wherever you can see VGS or VDS, you can substitute as input and output. And since substrate bias effect is 0, also we can assume that lambda is 0. So there is no channel and modulation parameter. Alright, so the threshold voltage of the MOSFET is VTO at 0 substrate bias. Alright, then we'll draw its VTC curve. How does it look like? So if you look at the VTC curve, it's a graph of plot of Vout versus Vin. Vin in the x-axis, Vout in the y-axis. So how does this graph look like? It looks something like this. It does not go to 0. It remains at a level that we call it as VOL. This is VOH. Then we take -1 slope and we plot one line over here and line over here. So these 2 points are called as VIL, VIH. Okay, at these 2 points will have the slope equal to -1. So dV out by dV in is equal to -1. And there is one more critical parameter, wherein if we draw a line which is having V out equal to V in, having a slope of 1, this is V out equal to V in line. So this slope is 1. Wherever it intersects the VTC curve, which is red in color, if I extend it down, this will be my threshold voltage of the inverter, VTH. Remember to distinguish between the threshold voltage of the inverter and threshold voltage of individual device, that is a NMOS device. Okay, so this is my NMOS driver. Okay, and this is my resistive load. Now what is our aim is? Our aim is to find out the expressions of the following of VOL, VOH, VIL, VIH, and probably the noise margin level, noise margin high, noise margin low. Alright, so from this discussion, let us start. We have already seen the operating regions. We have written the operating regions of NMOS driver last time, correct? Yes or no? And under steady state condition, we can also write over here that IRL is same as ID. If you apply KCL at node D, you will get the load resistance current is equal to the drain resistance, drain current in the MOSFET. Alright, so can we start with the actual derivation, that is expression for VOH, VOL, VIL and VIH. Alright, we have last time also seen working with numbers, and we have justified in which region the NMOS driver is operating in. Okay, so can we start now? Let me write those conditions. Yeah, so what were those conditions? The table we have drawn, one input range, right? One table, input voltage range, and we are correspondingly written what is the operating mode of the NMOS driver. So what was the range of input? V in less than VTO. So V in is nothing but VGS. So this was nothing but VGS less than VTO. That means my transistor is in cutoff mode. Okay, next range is V in is greater than VTO but less than V out plus VTO. So let us check this range now. So that means it is VTO less than or equal to, what is V in? V in is nothing but VGS. VGS plus V out is VDS, right? Plus VTO. So the same thing can be written as VGS greater than or equal to VGS greater than or equal to, what can we write? VDS plus VTO. Okay? Yes. Actually, yes, we could have written 0. It's fine. So here it will be 0. V in greater than 0. So here it also should be 0. So VGS is greater than, we can say, okay. So from here we can rearrange this and call it as V in is less than V out plus VTO. Yes or no? Oh, sorry, very sorry. It is VTO only written over there. There are two cases. We have divided into two parts. Yeah, I missed that point. So in the first case, V in is VGS, right? Let me write that VGS. Here it is less than, V out is VDS plus VTO. Here also it is VTO. So this is split up into two conditions. The first condition is this and the second condition is this. So the first condition, what do we have? VGS greater than or equal to VTO. So this condition is satisfied. Next condition is what? VGS less than VDS plus VTO. So we can say VDS is greater than VGS minus, we can write over here this is less, yeah, VDS greater than VGS minus VTO. Yes or no? So this is the condition for saturation. So in the second input range, my NMOS driver acts in the saturation mode of operation. Let us check the last range over here. I think it is clear to you now. V in is greater than or equal to V out plus VTO. So how can we write the statement again? V in greater than or equal to V out plus VTO. So V in is nothing but VGS greater than or equal to VDS plus VTO. So here we can say VDS is less than or equal to VGS minus VTO. So this condition is true for linear mode of operation. Alright, so we can say NMOS is working in the linear mode of operation. So that is how we complete this input range and NMOS driver operating region conditions. Okay, so with this knowledge, let us find the expression for the VOH first. So let me start. Let me go to the next page. So first we'll find VOH. So VOH estimation. Okay, so how do we start? We have to relate our VTC curve. So let me quickly draw the VTC curve. This is V out, this is V in, and we identified a VOH block over there. So here it is. Rest we will concentrate later. So this is your VOH. Okay, so what we can say over here, for the input voltage is very low. So here correspondingly for input value which is lesser than VTO, here we can say Vin is less than VTO. Okay, very much less than VTO. So for a very small values of input, my NMOS driver becomes off. So here we can say for small input voltages, that is Vin is less than VTO, that is VGS is less than VTO. So what can we say? My NMOS driver is off. So what do you mean by NMOS driver being off? So if it will act as a open circuit basically whenever it is off. So we have a resistor, alright, then we have V out over here. NMOS transistor off means it will behave as an open circuit. So this is NMOS being off. Now tell me, would there be a current flowing in the circuit? Yes or no? Will IRL flow? Just simple answer can you give me? Yes or no? This is ID. In the cutoff region, will the current ID and IRL exist? Can you just confirm? Yes, no, what? No. Because NMOS driver is off, that is your ID is 0. Alright. Now, under steady state, and also there will be no voltage drop across RL. Alright. Because IRL is also equal to 0. So, under steady state conditions, can we say IRL should be equal to ID? In this case, it is ID off. So, what is IRL? Can you tell me from the diagram? What is IRL? VDD minus V out upon RL. Yes or no? That is VDD minus V out upon RL, and ID of is 0. Are you agree to this? Yes. IRL is flowing through two voltage points, that is V out, VDD and V out. So subtraction of two voltages, VDD minus V out upon RL upon resistance is IRL. Now we push this over here. So V out is basically equal to VDD. And what is the V out value over here? V out value when Vin is very small, it's VOH. So we are actually estimating VOH. So that is nothing but V out equal to VOH. Okay. So instead of V out, we substitute VOH. So therefore we can say VOH of NMOS driver or resistive load NMOS inverter is almost equal to the supply voltages. Okay. So this is the estimation of VOH, output value, output high. Did you understand this now? The derivation, plain and simple. So this is VOH estimation. The VOH of a resistive load NMOS inverter is VDD, almost same as supply voltage VDD. Alright. Can we go to the next one now? So next is VOL estimation. So we need to refer the VTC curve. Let me show you the VTC curve once again. We'll keep on drawing this VTC curve because until it becomes a part of your system. Okay, so this is my VTC curve. This doesn't go to 0, it stays as some value, and this corresponding value at V out is VOL. This is VDD, sorry, V out, and this is V in. So to calculate VOL, now if you see carefully in this graph, we have to calculate the value of VOL, which is non-zero. To calculate VOL, we assume that input is very high. Okay, because VOL, as you can see, it's possible when input is very high value, it almost equal to VDD this way. So we can calculate VOL if input is almost equal to VOH, almost equal to VDD. When input is a high value almost equal to VDD, then we can calculate this VOL. Alright, so in that case, what is V out? When we are finding VOL, what is V out? Well, here we assume that V in is approximately equal to VOH is equal to VDD. So, yeah, again, I'll ask you the same question. What is V out in this case? This is to V in, right? V in is almost equal to VOH is almost equal to VDD. So, in that case, what is V out? Tell me the state. This is V out, na? So we can say if we, if we have to calculate VOL, we assume that V in is equal to VOH is equal to VDD here. X-axis is V in, right? So here, when V in is very high, my output is very close to 0. So here we can say V out is slightly above 0. Yes or no? See this part. So when V in is high, almost equal to VDD, my VOL is non-zero and it is just slightly above 0 point. Okay, so what is this value? Slightly above 0. So this is as per the VTC curve. As per VTC. Alright. So now how do we proceed forward? So therefore we can say here V out is slightly above 0. Okay, so what range we are talking about? So in this case, which is V out is very small, very small. In this case, linear mode of operation, right? So here VDS is V out, right? So V out is very much less compared to V in minus VTO. Okay, let's give you some numbers. You will understand when you give you some numbers. So let's say VGS is 1 volt, VTO is 0.5, and VDS is supposed to be now smaller than this. So tell me, when will be VDS less than VGS minus VTO in this case? Tell me the value. When will be VDS less than VGS minus VTO? Here. When it is around 0.4, right? This is 1 minus 0.5, which is zero point 0.5. So VDS has to be lesser than that. So what is V out? VDS equal to V out. So that means V out has to be lesser than 0.5 volt. Okay, here it is 0.4. We have example, for example. So V out is slightly above 0. That is, instead of 0 volt, you have over here 0.5 volt. I hope you got this point. So therefore, we can say that when V out is slightly above 0, we can say VDS is less than VGS minus VTO, as we have proved above. Okay, so therefore NMOS enhancement type driver is in linear region. Okay, why knowing the region of operation is important? This is important while they're solving the, deriving the derivation for, deriving the expression for the VOL. Now we can say, keep on writing please along with me. Under steady state conditions, under steady state conditions, or a condition rather, IRL is equal to ID linear alright. Now we substitute the value of IRL. What is IRL? From the last expression we have determined that it is VDD IRL. Again I'll tell you this. IRL is VDD minus V out. You can see this part, this blue color. IRL is nothing but this one. So it's VDD minus V out upon RL. So same thing we can write over here. VDD minus V out upon RL, and that is equal to, what is ID linear term given by? Kn by 2 twice VGS minus VTO into VDS minus VDS the whole square. Okay, so this is how we have written it. IRL is VDD minus V out upon RL, simple Ohm's law, but ID linear is not simple Ohm's law. It's Kn by 2 into twice VGS minus VTO minus VDS square. Alright, and now we can substitute the values. We can say substitute VDS, wherever you see VDS, substitute it as V out, which is nothing but VOL at the end, and also V in, substitute V in is equal to VGS, or we can say it's almost equal to VDD. Alright, so these two substitutions will make the derivation very smoothly. I hope you're following what I'm writing this. Yes or no? Now, what I will do is I'll rewrite this expression number 1. Okay, so equation number 1 will is given by, we can open the bracket and we can substitute it further. So it's VDD minus V out is actually VOL, so VDD minus VOL upon RL, which is equal to Kn upon 2 twice VGS is VDD, so VDD minus VTO into VDS, that is here in this case it is VOL, into VOL minus VDS square, that is VOL square. Yeah, any doubts over here? So we have replaced the terms VDS equal to VOL and V in equal to VGS equal to VDD. Okay, so let's proceed forward. So we can take this 2 over here, so it will be twice VDD minus VOL upon Kn times RL, which is equal to twice VDD minus VTO minus VOL square. Okay, the same thing we have written over here, that's it. Oh, there is one more term missing. What is missing over here? Can you tell me? VOL minus VOL square. That is what was missing. So actually we could open the bracket and solve this further, but it's okay. Now we can substitute in terms of a square minus 2ab plus c equal to 0. We have to rearrange in this form. What is a square? In this case VOL square. Okay, then minus 2ab, so minus 2 into this term VDD minus VTO. Okay, and there is one more term on this side also, right? So let me just bifurcate that. So this will be twice VDD minus VOL upon KNRL, and this will be twice VDD VOL minus twice VTO VOL minus VOL square. So this is the term what we have over here. Okay, so we can rearrange this as, that is VOL square, A square minus 2AB plus B square. So here we can substitute, take 2 common. It will be VDD minus VOL plus, now this term if you take it over here, this come to multiply this Kn into RL. So we can say plus VDD minus VOL term will come in common over there. VDD minus VOL it should be, right? VDD minus VTO plus 1 upon KNRL. Let me just write this down and then we'll come back to it, into VOL. So this VOL, this will come over here, right? Twice VDD minus VOL. Okay, actually this it's all right. Then will be plus twice VDD upon KNRL is equal to 0. Is it making any sense? Just check this out, this equation. Oh, sorry. Just check out this equation. Let's say if it is validated or no. So VOL square is taken care of. Then twice VDD minus VOL. Then twice VDD minus VOL. Here it is. One time it has come. Okay. So twice VDD minus VOL plus 1 upon Kn into RL into VOL. So 1 upon Kn into RL. Where does this term go? So here it is twice VDD upon Kn into RL. This term is intact. Oh, okay. We got it from here. See, this one. This expression has come. My VOL upon Kn into RL. This expression has come. Okay. So this is the VOL term. Are you getting it? What I'm saying? Then twice VDD upon Kn into RL has come over here. So this is correct. This is VOL upon Kn into RL. So this VOL is taken out, so this term has come. Okay, and here it is VDD minus VOL. Oh, so not VOL, sorry. Here it is VTO. So here you take twice VDD into VOL. Yeah, twice VTO. VDD minus VTO into VOL. So this twice has come, VDD minus VTO. This is correct. And here it is minus sign over already present, so it will be plus 1 upon Kn into RL. So VOL will take it out. Now it is, all the terms are satisfied. Yeah, it's correct. Are you understanding? So solving this quadratic equation will yield two values of it will give two values of VOL. Okay, and you have to take the physically correct one. Let's say, if example, if we get the value of VOL as, let's say, 0.1 volt and another value of VOL as 5 volt, which one will be correct? VOL is in the graph is where? Over here. It's very less value, about just about 0. So which one value will be correct? Tell me. VOL 0.1 or 5 volt? Quickly tell the answer so that I can proceed ahead. Yeah, please tell. Which value will be correct from the two ones? VOL should be very very close to 0, right? So which value is correct? This one, not this one. Okay, so you select this and proceed further. Now here the term Kn into RL is a very important design parameter. If you see carefully, in this expressions, VDD, VTOS is almost fixed. VOL we are finding it out, of course. Then VDD term is there, Kn term is there. Kn into RL term is again coming. So Kn into RL term is a design parameter that will determine the value of VOL. So this will help find value of VOL numerically. Okay, so solve this quadratic equation and find out the value of VOL. So this is the way it has to be done. Understood this technique? Hello, can you reply please? One of you. You understood how we did the derivation? Alright. So next we go for VIH derivation, the third one. VIL estimation. Okay, again I have to refer the VTC curve, so I'll draw it quickly. It won't take much time. This is V in, this is V out, and this is how our curve should look like. Okay, we have the value of VO. Now tell me, how do you measure VIL from the graph? So VIL is this minus dV out by dV in extended down. This is VIL. So this is nothing but dV out by dV in, that is the slope is equal to -1. We have seen that before. In fact, in the last lecture we have proved this point. So we have to find this value of dV out by dV in. And correspondingly, what is the value of output over here? Output is slightly below VDD. Okay, so we can say, referring to VTC curve, that is at V in equal to VIL, at V in equal to VIL, as you can see the output is slightly below VDD. Yes or no? So we can say V out at V in equal to VIL, my V out is slightly below VDD. Yes or no? So slightly below means what? Let's take some numbers. This might be 4.9 volt and this might be 5 volt. That's why we can say slightly below it. So can we say V out is approximately equal to, V out is approximately equal to VDS? Actually V out is VDS, we have determined that. It's almost close to VDD. 4.9 or 5 volt, it's both logic 1, right? So therefore we can say VDS is a higher value. So VDS is greater than VGS minus VTO. Let's say this is 0.5, this is 1 volt. Definitely VDS, which is a higher value, okay, that will be greater than VGS minus VTO. So therefore we can say NMOS driver is in saturation mode. Okay, you're getting the point? Output is slightly below VDD, so that means definitely VDS is also my V out, right? We have written that. So V out is the greatest, so that's why it should be greater than VGS minus VTO. Therefore NMOS driver is in saturation. Understanding or no? Now what do we now next write? Under steady state conditions, write down under steady state condition, IRL is equal to ID sat now, because we are in the saturation mode of operation. So what is IRL? VDD minus V out upon RL. And what is ID sat? Kn by 2 VGS minus VTO the whole square. Yes or no? So we have equated ID. Since why we are substituting ID sat formula? Because we have determined that NMOS is operating in the saturation region. That is why we are writing ID sat and not ID linear. Okay. So now we have to substitute over here. So substitute VGS equal to V in. So wherever do you see VGS, substitute by V in. So that is VDD minus V out upon RL, Kn by 2. Here instead of VGS we substitute V in minus VTO square. Okay. So this is what we get. We call this equation number 2. Now how to solve this further? We have to get the value of VIL. So can I say VIL is smaller of the two input values at which the slope becomes minus 1, right? So at V in equal to VIL, dV out by dV in is equal to minus 1, right? So we can say next now that dV out upon dV in is indeed equal to minus 1 or no. Okay, at which the slope becomes equal to minus 1. So let us proceed with this. So what do we do is we differentiate equation number 2, both sides of equation number 2 with respect to V in, because it is dV out by dV in. So the first term, what happens to the first term? It goes, okay. Then you're left out with minus V out upon RL, and minus V out, you already know that V out ka differentiation with respect to V in will be, this is 1 upon RL will come up, this VDD upon RL will go, and here you will get d V out by dV in. Okay, so it will be differentiation of right hand side will be, sorry, left hand side will be minus 1 upon RL. I have just isolated this term out, and instead we get V out, VDD minus V out. VDD is a fixed term, V out only matters, so it is dV out by dV in. Alright, on the right hand side, what do we get? Kn by 2 into, so this is twice, so twice x square will be 2x. Okay, so it will be 2 times V in minus VTO. Okay, and of course VTO is present, so its value is relatively constant almost. So the only variable is V in, so twice V in minus VTO. Okay, now next, that is 1 upon RL is equal to, now tell me what is dV out by dV in we have to put over here. So we can say set dV out by dV in equal to minus 1. Okay, so instead of dV out we write it as minus 1, and this minus gets cancelled. Let me write it formally. Okay, this will be Kn times V in minus VTO. So I'm trying to eliminate all the terms and bring in terms of V in and V out so that we can conclude. So it will be 1 upon this is RL and this is Kn. So Kn into RL is equal to, alright, so this is 1 upon Kn into RL. On this side, what do we have? V in minus VTO. Yes or no? So how can we rearrange in terms of V in equal to everything else? So V in is VTO plus 1 upon Kn times RL. So this is my value of V in. Okay. So what is my V in over here in this case? My V in is nothing but VIL. That is what we are finding. VIL. Sorry. VIL. So we can write here, this is my equation, of course. Okay, let me just do it properly. Okay, above part is not coming well. Okay, V in is equal to VTO plus 1 upon Kn into RL. Call this equation number 3. So value of the output voltage when V in is equal to VIH can be found out as follows. Equation number, we have equation number 1 where, yeah, here. No, equation number 2. Here it is. So what do we do now is, next is, the values of the output voltage when V in equal to VIL can be found out by substituting equation number 3 in 2. Okay, 3 in 2. So that means, let me write equation number 2 again. Let me write this equation number 2 again. So this is equation number 2 to be rewritten. It's VDD minus Vout upon RL is equal to Kn by 2 V in minus VTO the whole square. Yes or no? This is the equation we got. Now in this equation you substitute the value of V in equal to VTH. So V in equal, VIL. So V in equal to VIL is how much? So here it is nothing but VIL, VIL. So V in equal to VIL is equal to VTO plus 1 upon Km times RL. So substitute this value over here. So what do we get? Let's check. So VDD minus Vout, okay, divided by RL is equal to Kn by 2. Here we substitute the value of V in or VIL. So it is VTO plus 1 upon Kn into RL minus VTO the whole square. So from here immediately we can observation that VTO gets cancelled. Rest all the terms remain intact. Okay. So let us continue further. Sorry for that. I hope you have noted down up till here. That is, please complete your work till then. I'll give you 1 minute more. These are the derivations which will come, or you can understand this only by practicing. Nothing else. You cannot scan this and go in your exam for your exams. You have to practice it on paper without looking, and then we have to solve them. Okay. So what are we doing over here is we are finding the value of VIL. So for finding the value of VIL, we use the steady state equation that is given over here. Here it is. IRL is equal to ID SAT. We substituted the values. Then we substituted VGS equal to V in this equations. And now we are setting dV out by dV in equal to -1. Because that is what we have defined at, right? The slope should be -1. So dV out by dV in is -1. So now we differentiated this with respect to equation number 2 with respect to V in. So what do we get? -1 upon RL. dV out by dV in is equal to Kn by 2 into twice V in minus VTO. Okay. So here dV out by dV in equal to -1. We have to set. This should be equal to -1. Alright, so that's how the expression of VIL is. VIL is VTO plus 1 upon Kn times RL. Okay. Now for this value of VIH, what is the corresponding value of output? That is what we have to find. So here this is the value of VIL, and corresponding to this, if I extend it on the y-axis, what is my value of V out? That is what we need to find out, the expression. Okay. So what we will do is we'll substitute these values over here. Equation number 2 we have rewritten, and instead of V in, we substitute it as VTO plus 1 upon Kn into RL. Okay. And then we started opening the bracket and we got VTO as common, VTO as cancelling out. Then we can proceed it further. Even this we can write it separately. VDD minus V out is equal to, here we can shift the value of RL. So RL will come in the numerator now, and RL into Kn we can write, correct? VDD minus V out is equal to RL into Kn by 2, and here we have 1 upon Kn square RL square. Okay. So definitely some of the terms will get cancelled out now. So Kn square gets cancelled with Kn. RL gets cancelled. RL square gets cancelled with RL. Okay. So what is the stance now? VDD minus Vout is equal to RL. One term of RL is there in the numerator. So all the terms are in the numerator, no term is there in the denominator. So uh, it will be twice Kn into RL. That's it. Okay. Now we rearrange the bracket. What is Vout now? Vout will be equal to VDD minus 1 upon twice Kn RL, and that's the expression for Vout. We know it that it will be closer to VDD, but just we are making sure that it's correct. It will be closer to VDD only. Okay, Vi the corresponding value of output voltage when input is equal to VIL. Okay, so here we'll find out the value of here found out the value of Vout, and this is done at for Vin equal to VIL. All right. Okay. So the expression is clear to you. So if we know the value of VIL, we have to know the value of Vout also. Same is the case with VIH derivations. So can I proceed further now? Hello. The fourth one, VIH estimation. So let us start with the VIH estimation. Okay. So again we'll draw the VDC curve. You have to draw it every single time. V in, V out, wherever you're explaining such answers. So the graph will be like this. Okay, and we have to find VIH. VIH is the higher critical parameter. So here it is the value of VIH. If we draw a tangent over here, so this is VIH, and here the slope is -1. And what is the slope? dV out by dV in. So that is equal to -1. All right. So VIH, this is the VIH corresponding value. Okay. So we can say at V in equal to VIH, what is my output status? My output V out is where it is? Here, na? Where it is? Output V out is slightly above 0. Is slightly above 0. Okay. So output is nothing but VDS, right? Output is nothing but VDS. If VDS is very small, that means VDS has to be lesser than VGS minus VTO also. Itna small ho gaya. Okay. So this is the condition for which this is the condition for NMOS driver to be in linear saturation or cutoff. Tell me. What is this device operating in now? Tell me fast. These are important numericals or the derivations. What is the status? NMOS is in linear mode of operation. Okay, so please remember that. Because V out is slightly above 0. Maybe this is 0 height. Maybe it is around 0.8, 0.9 volts. That, you know, that's not harmful. So we will estimate further. Can I go ahead now? So now we can say under steady state conditions, what can we write? We have written to only one formula again and again. So IRL is equal to ID linear. Okay. So and what was IRL? IRL we written many times. From the circuit diagram it is, here it is, VDD minus V out upon RL. IRL is VDD minus V out upon RL. So it will be, that is VDD minus VDD minus V out upon RL is equal to Kn by 2 twice VGS minus VTO into VGS minus VGS square. Okay, now you can substitute still to make it less complex. Substitute VGS is equal to V in and V out is equal to VDS. Okay, fine. So substitute in the above expression, what do we get? And what are we finding? Don't forget VIH. So that is VDD minus V out upon RL is equal to Kn by 2 twice VGS is V in. So V in minus VTO minus VDS is V out is equal to VDS. So wherever there is a VDS term, here VDS will come, right? I am surprised no one has. This is VDS square. You can check it out later. Okay. So now we are getting, after substituting twice V in into VTO into VDS, right? Or V out. Okay, why I am writing V out? Just you can check, V out is equal to VDS. In the very first slides we have written it for today. See, one of the condition is, let me check. Yeah, VDS is equal to this thing. So these are the conditions. Just see. Yeah, see, V out is equal to VDS and V in is equal to VGS. We can interchangeably use that. So let us carry on with the derivation. So it is V in minus V out minus VTO into V out minus V out square. Okay, this we call it equation number 4 or 5. Yeah, we can call it equation number 4. Alright, now VIH is the larger of the two voltage points. VIH is the larger of the larger of the two voltage points on VTC curve at which slope is equal to -1. So that is V dV out by dV in is equal to -1. So for that we have to differentiate equation 4 with respect to V in. Okay. So what's the first term over here? First term will be, let me mark the first term. The first term will be V out upon RL will disappear because they are constant, so it will be -1 upon RL, and here we have dV out by dV in is equal to Kn by 2 twice V out, because it is a multiplication, right? So multiplication of derivative we can find, so it is twice V out plus twice V in minus VTO into dV out by dV in. Okay, minus what is integral, what is differentiation of x square? It is 2x, so 2 into V out into dV out by dV in. Okay, so the differentiation is ready. Now how do we find this point finally? Finally we find the value of VIH by taking the slope equal to -1. So now you substitute, you can say next we set dV out by dV in as equal to -1 in the above expression. So what do we get? Here -1 upon RL into -1 will become 1 upon RL. Here on the right hand side we can take 2 is there inside, so 2 and this 2 will get cancelled out. So you have Kn into this term. We are considering dV out by dV in, right? dV out by dV in is over here. So Kn into twice V out, okay, plus V in minus VTO. You can check this V in minus VTO. Yeah, V in minus VTO, because this is minus 1 and this is also minus 1. And yeah, I think that's it. You can close the bracket. Okay, so twice V out plus V in, twice V in actually, V in minus V out, V in minus VTO it is, sorry, 2 we have already taken out. Okay, still it is twice V out because this and this is cancel, this and this we are adding it up, because this is minus 1, right? Let me do it conventionally because I think this is the way. I'm skipping one step, you are not able to follow then. Okay, so now let me write peacefully. So first is 2V out, let it be by 2, plus so this we have substituted as minus 1, so it will be minus of twice V in minus VTO. Here it will be plus 2V out, dV out by dV in is what? Minus 1, so it is equal to minus 1, so this will be plus. Yeah, now it's correct. Now you can take this common, so 1 upon Kn into RL is equal to minus, this 2 will disappear and left out with the terms as 2V out, this is plus, then we have minus V in plus VTO. So this is the expression we get. So we can say V in is equal to VTO plus twice V out plus 1 upon Kn times RL. So this is a new equation, equation number 5. Okay, so we got the expression for V in, which is nothing but VIL. We at the end we can do it. At the end we can substitute. Now here we have the value of V out, so we have to next find the value of, so this is V in equal to VIH. Okay, so next a task is to find the value of V out, find the expression for V out. Why find expression for V out? Because for V in equal to VIH, we have to find the value of V out. What is the corresponding value of V out? Here we have written 0.8 for example. So let us find the value of V out. So how do we find it? We substitute this equation number 5 into equation number 4. Here, this one. Okay, I know it will be a tough ask, but we have to do it. So let me rewrite this expression number 4 again. You have to find the value of V out. So this will be, that is VDD minus V out upon RL is equal to Kn by 2 twice V in minus VTO into V out minus V out square. So basically here wherever you have a V in term, you have to substitute it over here like this. Okay, so let's do that. So it will be VDD minus V out upon RL is equal to Kn by 2 twice we substitute the value of V in, so V in is nothing but VTO plus twice V out plus 1 upon Kn into RL. Here it is minus VTO. Now this term will come as it is, right? Minus VTO. So this entire thing expression was equal to V in. So V in was equal to these terms. Yes or no? Then minus VTO will come, and that is multiplied by V out minus V out square. Okay, so what gets cancelled out over here? VTO terms gets cancelled out. So let us rearrange the terms. So what do we get over here? This 2 we take it on this side and Kn down. So we get twice VDD upon Kn into RL minus twice V out upon Kn into RL. On this side, what do we have? We have the value of Kn. So inside Kn, what do we have? We have, okay, let me write this expression again. So this is twice V out into V out. That will be um, 2 into 2 V out square, okay, plus 2 divided by Kn into RL, 2 V out divided by Kn into RL, and oh sorry, here Kn into this will not come because we have already taken it over there on this side, minus V out square. So from here we can easily carefully see that this term and this term gets cancelled out very easily. Okay, here we are getting 4 times V out square, and here we are getting V minus V out square, so it will be 3 V out square. So finally we get twice VDD upon Kn into RL is equal to 3 V out square. Okay, so we can write V out is equal to square root of 2 by 3 VDD upon Kn into RL. Alright, this we call it expression number 6, and this is happening at Vin equal to VIH. I think these are the derivations which are the VIH and VIL derivations are quite, something. So now substituting this equation number 6 in equation number 5. So let me write expression number 5 again. So expression number 5, we rewrite it Vin equal to VTO plus twice V out minus 1 upon Kn into RL. Okay, now this is the equation number 5. So substitute this expression number 6 over here, this one here. So that will eliminate V out. So we can write V in, or we can call this as VIH now. So V in equal to VIH, it will be equal to VTO plus twice square root of 2 by 3 VDD upon Kn into RL minus 1 upon Kn into RL. Okay, so this VIH finally will be, if I take this inside, it will become square, so it will be 8 by 3, so it will be VTO plus square root of 8 by 3 VDD upon Kn into RL minus 1 upon Kn into RL. So this is my final expression for VIH, which we call it equation number 7. I know it's very lengthy, but that's the only technique which we can follow to arrive at this step. Okay, so let us summarize. We have first got the expression for VOH. VOH was actually equal to VDD. Then we have gone and got a quadratic equation for VOL. From here we can find any, from the two values we can find one value which is closer to the real parameter. Then we have done the derivation for VIL and got the answer in this form. VIL is VTO plus 1 upon Kn into RL, and finally VIH, we got the final expression in this form, VTO plus square root of 8 by 3 VDD upon Kn into RL minus 1 upon Kn into RL. So these are the 5 critical parameters expression, and now once we know them, we can easily find the noise margin levels. So what are the noise margin levels? We calculate them in numbers and then calculate and noise margin low, which is VIL minus VOL, and noise margin high means VOH minus VIH. Okay, fine. Then there is one more which is left out, which we have to do it quickly. Remember, we have 5 critical parameters which are there: Let me go and show it to you. VOH, VOH, VOL, VIH, VIH, and VTH. VTH is also left, threshold voltage of the inverter. So let's calculate threshold voltage of the inverter now. I hope you are there still. Yeah, this will come with practice. You need to practice in. Now we'll estimate VTH. So VTH estimation. Let me put it into full screen mode. So for VTH estimation, let me draw the VTC curve to get a clear picture. So this is V in, this is V out, this is my VTC curve. Where is V in versus V out curve? So whenever we have a line which is passing through the origin, which is the line V out equal to V in, this point it intersects the curve, extended down, extrapolated down. This is your VTH of the inverter. Okay. Alright. So VTH is actually called as inverter NMOS, resistive load inverter threshold voltage. So we can say at this voltage level, we can say V in is equal to V out. This is the line which we have with a slope of 1. So V in is equal to V out, which is equal to VTH. So this is what is really important. And over here, since let's take some numbers. Let's say VGS, which is equal to V in, is 2.5 and VTO is 0.5. Okay, and output VDS is equal to V out is at 2.5. Let's say this is VDD. So this is exactly in the middle, let's say. So now what equation will suit? Now VDS should be greater than VGS minus VTO. Which condition is satisfied? So VDS is 2.5, VGS is 2.5 minus 0.5. So yes. So here we can say my NMOS driver is in, because if we take it less, it cannot be less, right? It has to be greater. So here we can say we have to see, for finding the value of any critical parameter, we have to find which active region the resistive load inverter is in. So NMOS E driver transistor is in saturation region. Okay, so here again we can write under steady state conditions, we can say IRL is equal to ID sat. Now remember, we have done this before. IRL is VDD minus V out upon RL, and ID sat is Kn by 2 VGS minus VTO the whole square. So instead of VGS, we can substitute it as V in. Okay, since V in is equal to VGS, at least for this part. So now we substitute V in is equal to V out is equal to VTH. Okay, so wherever you see V out, we can substitute it as VTH. Wherever you see V in, we substitute it as VTH. So that is VDD minus VTH by RL is equal to Kn by 2 VTH minus VTO the whole square. Alright, we take this over here, so we'll get twice VDD upon Kn into RL minus twice VTH upon Kn into RL is open the bracket over here, A square minus 2AB plus B square plus VTO square. Okay, so here we can rewrite it as VTH square minus twice, wherever there is a term of VTO, we can combine that VTH expression. So VTH is over here and here, so we can combine twice VTO plus 1 upon Kn into RL into VTH minus, where are the terms which are without any VTO minus twice VDD upon Kn into RL. Yes, understood this expression? So we need to solve this quadratically in your calculators. So this will give you the two values of VTH. So whichever is the closest to VDD by 2, that value you select. Okay. So let's say one value is 2.7 volt, other is 3.1 volt. Which value will select for the power supply of 5 volt? Okay. So you will select the value of 2.7. Why? Because it is closer to VDD by 2. Alright. So select the correct value of VTH. Now in summary, if I want to describe the entire behavior of the NMOS operating region, so let's start. I hope this is clear. VTH derivation is clear to you. We leave at this and we have to find two quadratic this is the quadratic equation. For that will give you two values, so you have to select the physically correct one. Now summary, let us revise what we have done so far. First of all, let me draw the VTC curve again. You have to draw it, keep on drawing it again and again and again until it becomes part of your system. Okay, so this is my VTC curve. It doesn't go to 0. So this is VOL, VOH, then here we have VIL, VIH, and this is the line passing V out equal to V in line. So whenever it intersects, we write that point. This is VTH. So you have to estimate the, we have to write the summary now. V in, V out, NMOS operating mode. Now V in is less than VTO and output is at VOH. So what is my operating mode of NMOS? Can you tell me? Where am I over here in the graph? Very low values of input. Okay, input is very small. So what is, and output is VOH, almost VDD. So which operating region my NMOS is operating over here? V in is less than VTO. So that means it's cut off, right? Second, V in is VIL, output is almost equal to VOH. V in is equal to VIL here, okay, and output is almost equal to VOH. So what it is? Which region of operation it is? Saturation. Now, if this is VIH, input is VIH, what is output? Almost VOL, almost very small. Yes or no? So this is linear mode of operation. Then this is VOH. Input is VOH, very high. My output is equal to VOL here. And again I am in the linear mode. And lastly we are at VTH. Input is at VTH. Output is at VTH, and saturation region for the NMOS driver, because it is operating at its maximum capacity when you are in this condition. So that is VTH, input and output is VTH, then the NMOS driver is working in the saturation region. Understood this? Any doubts or queries related to the topic? Quickly ask. Hello? Do you have any doubts? Okay, so this is the end of lecture number 40. We'll take 2 minutes break and we'll start with lecture number 41 shortly based on the numericals. Alright, so we'll resume in 2 minutes time.